Hello, this is Mr. O'Brien again. This is going to be part two of the lecture series, The Periodic Table. In this lecture, we're going to cover the information in section 6.2 from your textbook and 6.3. And the idea here is to emphasize characteristics that we can predict. So again, we're going to emphasize characteristics that we can predict. Some of these might be new and some of these might be old, so let's see how much you know. Starting with the first one. So the characteristic number one is valence electrons. The two towers of the periodic table really is the result of the emphasis of valence electrons placed on organizing these elements into a certain grid. And if you look at the periodic table has group number 1A as one valence electron. These dots have one valence electrons apiece. Now these dots might be in different orbitals of these atoms, but again, what's common about them is their number of valence electrons. So again, here's 2A. They have two valence electrons. This is 13 or 3A, and this is 14 or 4A, 15 or 5A, and 16 6A, and 17 7A, and then finally 18 8A. You can see as you go from left to right on the periodic table, the number of valence electrons increase up to 8 valence electrons, with the exception of helium, because helium is in period 1 with one orbital. You can only fit 2 electrons, right? So, with that said, do you notice what occurs with the valence electrons when transitioning from neon to sodium? So we have 10 protons, 10 electrons here. What happens when you go from neon back down to sodium? Well, you can clearly see that the number of electrons goes away, right? You end up losing 7 electrons and starting off from scratch again. This pattern, this trend, does the same thing from left to right as you go to the next noble gas. And when you get to argon and you add another electron, it jumps back down to 1 valence electron. So again, this pattern is the same from left to right across a period on the periodic table, right? So consider this question. How is the energy level of the atom's valence electron related to the period the element is on the periodic table? So how does the period numbers, the ones here on the left-hand side, reflect the atom's valence electron? So answer that question. If you have a hard time, hit me up at tutorial, okay? So we saw a video about atomic radius, and more importantly about atomic radius, this effect of Coulombic attraction, which is illustrated here on the bottom, in which the Coulombic attraction is this attraction between negative particles and positive particles. And the negative and positive particles that we know of are the electrons, and the positive is going to be the protons, right? More specifically, the nucleus, right? Now, the video tends to show us that as the electrons get closer to that nucleus, the amount of attraction increases. It's kind of like having a magnet. When you have a magnet and you place that magnet next to a refrigerator, right, to put on your like pictures and stuff like that, you know, that you have, or the things to do. As that magnet gets closer to the refrigerator, you're going to start feeling more of a force pulling that magnet closer to that refrigerator. Now, why is that force not felt the further away you are from the refrigerator? Well, it's because of this Coulomb's attraction. The attraction becomes less. When you feel less force, there's less Coulombic attraction. And that Coulombic attraction has to deal with the atomic radius. So let's continue on with this idea of atomic radius. So atomic radius is based on two factors. One is the orbital, and one is this, again, Coulombic attraction, which we call nuclear attraction. So the orbitals are these levels that the electrons fly around, right? At a simplistic view, right? And these electrons, these little blue dots right here, represent, again, the electrons. But we have inner electrons, and then we have the valence electrons, which we call the outer ones. And those are the most important ones. And notice that the valence electrons are attracted to the nucleus, right? This attraction, this Coulombic attraction, right, pulls those electrons closer to the nucleus. But it's kind of hard for that valence electron because most of the love comes from these guys. The inner electrons really attract more of that pull than that electron on the outside. But that's okay because it still gets some, okay? So let's consider some examples so we can understand a better idea. Well, If we compare the size of lithium, right, with the size of a cesium, you may already know that based on the Bohr model, right, that your simple drawings, no matter how bad they might be, are going to show a big difference in atomic sizes, right? A big difference in the radius. There's a bigger radius here with cesium than there is with lithium. And that's because, again, there's more orbitals for cesium. But what happens when you compare lithium with one of the elements in the same period, like fluorine? Well, we end up finding out that the Coulombic attraction actually plays a big factor here. And that means that because we have 3 protons in this nucleus for lithium and these 3 electrons, 2 of those electrons are on the inner electron and 1 of them are on the outside. And so these 3 protons really try to pull that electron in closer to the nucleus. But the reason why it gets smaller for fluorine is because now in fluorine you have 9 protons. Notice that the number of shells don't increase, so those valence electrons are relatively in the same shell. But it shrinks because we have now more positive pull. We have more positive in that nucleus, right, pulling on this little electron on the outside, or a lot of electrons on the outside. Again, there's more Coulombic attraction present, right, and hence we shrink the atom size. So we get bigger going down the group, and we get smaller as you go left to right. Now you can see this example on this big picture here of atomic radius. Again, we're omitting the transition metals. They're not here, right? Because we can see the gap here between 2A and 3A, right? And so you can see that although the difference can be seen from left to right, it's not so clear when you compare ones right next to each other. And that's again because the Coulombic attraction shrinks just a little bit, right? It pulls a little bit because they're the same energy levels. But as you go down, right, from top to bottom, you can definitely tell that the orbitals increase in the shells. So keep that picture in mind and answer these questions about atomic radius. If you have a hard time with these questions, hit me up at tutorial and then we can go over them together. The next idea of characteristics that we can predict is something called ionization energy. And ionization energy, the key word here is ions, right? It's the energy required to remove an electron from an atom to form a cation. We'll talk more about what a cation is in a second, but keep in mind it's an ion. Now think of ionization as how strong, right, an atom is, right? How strong is it, right? Now, how is the strength anything based on? Well, and if you look at this image here from our video that we saw in class, the electrons are being pulled away from the atom, in this case now from a cation, an ion. So notice how the electrons are pulled away. Now, there's a certain amount of energy that needs to be used to pull that electron away. Now, why? Because that electron's already hooked up to this atom, and it's attracted by this, remember, Coulombic attraction. So how do we break that Coulombic attraction? Well, we have to give it some sort of energy. And that energy to break it is called that ionization energy. Now, let's talk about really what a cation is. Now, think of the word cation and take a look at the T on cation and the ion. Think of the word T as positive ion. Now, why is it positive ion? Well, in lithium, you have 3 protons and you have 3 electrons, right? But the ion of lithium, the cation of lithium, still has 3 protons because it's still lithium. But it's a positive ion because we've removed an electron, or somebody has removed an electron. Now, you might be wondering, well, who's that somebody that removes the electron? It's a great question. Keep that in mind on the side. So when we talk about ionization energy, we really talk about, it's really based on the size of the atom. This is a big piece. And really, it's the distance of the valence electron is from the nucleus. Just like we talked about Coulombic attraction, the closer the electron is to that nucleus, the more energy it has, the more attraction there is between the two. The further the electron is from the nucleus, right, the less Coulombic attraction there is, right? And so because there's more Coulombic attraction here, it's going to require more energy to break that up. Because there's less Coulombic attraction here, it's going to require less energy to break that up. Let's kind of understand this in an example for aluminum. So here's an aluminum atom. And this aluminum atom, as you may know, and if you don't know, you can have a periodic table out. It contains 13 protons and it contains 13 electrons, right? We know that it has Al plus Al with three electrons. Now, if we take a valence electron away from the atom, it's going to require X amount of energy. That X amount of energy required to take that electron away is noted here. Now, notice what happens with the size. The size shrinks. Well, why? Well, now the Coulombic attraction is increasing. There's more Coulombic attraction here, right? Because we still have 13 protons, but we only have now 12 electrons, and that's why there's a +1. So how do we take out this electron here? We'll add even more energy to pull it away because it's so close. About 3 times as much energy. We have 13 protons still, and we now have 11 electrons because now we have a +2. Well, there's still valence electrons here. There are valence electrons here. Well, we add even more energy to pull that electron away, about 4 times as much from the original, even more. And then it gets us 13 protons and 10 electrons. Now, can this electron still be taken out? Well, yeah. Now, remember that the atom of aluminum has 2 electrons here, 8 electrons there, and 3 electrons there. So we've really gotten rid of the whole valence electron of 3, but there's still 8 electrons here present. And these 8 electrons present here can still be removed. Now, if we take a look at this example that I have here, the question gives us a graph of the amount of ionization present in taking away the first electron, and then the second one, and then the third one, and then the fourth one. Take a look at the amount of energy for the fourth one. Well, why do you think it increases? Well, we already talked about why it increases, because that valence electron gets closer and closer and closer. It's the size, right, that makes this even harder to take electrons away. But why does removing the fourth electron is so much more energy, requires so much more energy than the third one? Well, look how small it is compared to the third one, right? That's a big difference there. And not only that, we're now talking about a second orbital, right? So again, size is that big issue, right? It's really hard. The more you take electrons from the atom, it's harder and harder to take each successive electron away. Okay, let's move on to the next question, or next point. Here's a pattern of ionization energy. Helium is the smallest atom on the entire periodic table, and francium is the biggest, and so hence the valence electron here is further away. The valence electron here is closer to the nucleus, and that's going to be harder to take electrons from. That's why the ionization increases. So take a look at these questions about ionization energy, and if you have any questions on it, let me know at tutorial. The next trait that we looked at is electronegativity. Now, electronegativity measures the ability of an atom to take away electrons from another atom. And if you look at this example, this little clip from the video that we've seen, notice that chlorine is essentially taking away an electron from sodium. Okay, now why is that? Well, it seems that chlorine has been granted a certain amount of electronegativity that sodium doesn't have. Well, we know that sodium doesn't have that much electronegativity because it doesn't pull electrons away. As you can see, it loses those electrons. When certain elements come next to other elements, their electronegativity, their ability to take electrons away, starts to play a big factor of who's going to become what type of ion. Now, when we think about electronegativity, we think about anions, a negative ion. Key way to remember that, a negative ion. So in fluorine, if you have 9 protons and you have 9 electrons, right, this becomes a neutral atom. But when an electron is gained, because fluorine is so attractive, it's going to now have 9 protons, same thing, but 10 electrons, and so hence the negative charge comes from that extra electron. Electronegativity is really based on something called a Pauling scale. Now, it's a kind of theoretical value. It's not experimental. It's a theoretical value. And the more electronegative the element becomes, the higher the Pauling value is. So if you take a look at fluorine, that has a Pauling value of 4.0. But as you go left, that Pauling number shrinks. So what does that tell you about the pattern that you notice in the periodic table? Well, from left to right, the electronegativity increases, right? So the trend increases from left to right. Now, there's a little catch, though, because these noble gases don't seem to have any electronegativity. A question we'll hit up in a second. As you go from top to bottom now, in the groups, that electronegativity drops. So from top to bottom, right, the electronegativity decreases, right? Now, why is there no electronegativity values for gases? Well, remember, when you're a noble gas and you have 8 valence electrons already, like neon, let's write neon, right? 8 valence electrons. If you gain an electron, remember that you jump all the way back down to sodium, Na. And you don't want to be like sodium because now you start off from scratch again with 1 electron. So noble gases have no attraction for electrons because they already have a full shell of valence electrons. That's a key point to understand. Now here's a pattern for electronegativity across the periodic table, the same idea that we've hit up with noble gases. And the lowest one is cesium, actually francium, the bottom left-hand corner. Now, what are some predictable characteristics of ions? Now that we talked about ions. So in ions, with regard to ions, there's 2 different types of ions that are created. Metals tend to form cations because they have really low ionization energies, right? Their valence electrons are far away, and so the attraction is less. And so they end up losing electrons, okay? The right-hand side, however, are the nonmetals. They tend to form anions because they have high electronegativity. They attract electrons. So here's your chlorine atom. The chlorine atom is so attractive that it gains electrons. Now, notice how the size of the anion increases versus its atom. But here, the size of the cation shrinks, right, compared to its atom. So this is an important piece of note about the size difference that exists here. And how do you predict these? Because you can also predict certain types of elements, of ions. And these guys don't want to lose or gain electrons because they have a full shell. But fluorine's got 1 more electron it needs only 1 more electron to be like a noble gas. So it will attract valence electrons. Same does oxygen. Not as much as fluorine because oxygen needs, if you notice, 2 more valence electrons, right? So anything in this column is going to be a -1 because it'll gain 1 electron. But anything in this column is going to be a -2 because it gains 2 electrons. And these guys, which are still nonmetals, they'll gain 3 electrons. So anything in this column will be a -3 ion. And these guys really don't count because they're 4 valence electrons, right in the middle. But if you look on the left-hand side, this alkali metals, these guys lose an electron, right? Because they're so close to becoming a noble gas, right? And so these guys will end up becoming a +1. These guys here have 2 valence electrons, and they'll lose those 2 because they're very weak, right? Low ionization energies. And as they lose them, they'll become like noble gas again, be a +2. It's this idea that atoms want to be like a noble gas, and they'll fulfill a rule called the octet rule. They will attempt to gain or lose electrons to get a full set of 8 valence electrons. Obviously, except for helium, of course. So here, why does this guy gain 5 electrons? Why does he only lose 3 for boron? Well, because again, he's a metal, right? And they lose electrons. It's a lot easier to lose 3 electrons than to gain 5. It's a lot easier to gain 1 electron than it is to lose 7 because he's so close to becoming a noble gas. So take a look at these problems for cations and anions. See if you can figure this out. And here's some more pictures of an ionic radius, right? When we talk about -3s, -2s, -1s, the type of ions these atoms inform, right? +1s, +2s, +3s. If you have any questions, hit me up in tutorial.